Hello everyone. So I'm back with another video with the same topic, NMR spectroscopy. So those who have not watched the part 1, please go back to my channel and watch the part 1. So let's start with the part 2. Let me share the screen. So as I have already explained in the part 1, I'm going to teach here the NMR spectroscopy, which is needed for research. I'm not going to discuss the theoretical aspects of NMR in this series. Maybe I'll make a separate series on that. So here are some links about myself. You can check my LinkedIn profile, Google Scholar, and ResearchGate profile for details of my research area. So let's start with the part 2 of the NMR spectroscopy. So how to analyze NMR signals? I have already discussed point 1 in my first video. Now I'm going to discuss the point 2, which is chemical shift. Which is chemical shift? Like in the NMR signal, you will see there a certain distinct peak shift for each peak. Some will be 1, 2, 3, 4. It's up to 14, I could say, which is written in delta. Unit is ppm. So the particular type of proton has a unique chemical shift value. So you will have an idea which type of proton it can be from its chemical shift value. So here you can see the table. The chemical shift value can be from 0 to 12, even up to 14, I would say. Usually we check from 0 to 14. So this is a widely, this is a general idea about the type of protons. This is not very specific, I would say. So from this region, usually 1.5 to, I would say 5.5, there are characteristic of aliphatic protons. From 6 to about 9, that will be aromatic protons, and from 9 to 12, 13, 14, that can be acid, aldehyde, etc. Now, to be specific, let's look at this table. So if this is a simple alkyl group, RCH3, the chemical shift will be 0.9. For alkyl RCH2R, it could be 1.3. For alkyl R3CH, it could be 1.5 to 2. For allylic protons, with this structure, this allylic, the protons attached to the carbon next to a pi bond. That means I meant these protons. It will be, it will have a chemical shift value of 1.8, and then which has the protons which is attached to a carbon with a carbonyl group, that will have chemical shift value around 2. For benzylic protons, it will be 0.3. For alkynyl protons, it will be 2.5. If it is alpha to the nitrogen, it will be around 2 to 3. If it is alpha to the halogen, it will be 2 to 4. Alpha to oxygen, 3.8. Alpha to fluorine, 4.5. Like this. And this table is continued. Vinylic, as you can see, the proton attached to a alkene carbon, which is this, it will have a chemical shift value of around 5. For aromatic protons, it's the range is 7 to 8, but I have seen like it can range from 6.5 to 8.5, I would say. The aldehyde protons, it will be around 9 to 10. Alcohol, it can be 0.5 to 5, or even maybe greater than that. For phenol, it would be 4 to 7. Carboxylic acid, it has higher, it has high chemical shift value. 10 to 13. For amine, it would be 0.5 to 5. For aniline, it could be 3 to 5. For amide, it could be 5 to 9. But let me tell you that these chemical shifts values are not very specific, I would say. It depends upon the chemical environment, the typical chemical groups or subgroups or functional groups. It changes the chemical shift value little bit. Also, depending upon the different type of NMR solvents, these values change as well. So now, but you will have an idea from the range, like which type of proton you are getting. So in the NMR software, you will have an option to integrate the specific peak. Once we have identified, let's say this is aromatic carbon, this is for the aromatic protons, then we will integrate that particular peak. There will be an option to integrate in the NMR software. So you have to select the specific peak and integrate it. And as I have already mentioned, that these chemical shift values change depending upon the chemical environment, also depending upon the NMR solvents. So now each peak, it splits. It will not be like a single peak. It will be generally a multiplet. So it can be a singlet, doublet, triplet, even up to sextet, anything. It can be a multiplet. So you will have an idea about the splitting of the signals by looking at the adjacent carbon atoms. So there is a rule for the splitting of the signals. The multiplicity of the peaks is n plus 1, where n is the proton number on an adjacent carbon atom. So let's take a very simple structure, CH3, CH2, CH2, Cl. So we have three different type of protons here. Now let's take this A. It has 3 protons attached to it, and the adjacent carbon atom, it has 2 protons attached to it. So from this n plus 1 rule, so for this A protons, the splitting of signals will be 2 plus 1, that it will be a triplet. Similarly for B, it will be 3 plus 2, 5 plus 1, sextet. For C, it will be 2 plus 1, triplet. And when you integrate these particular signals, you will see that the triplet is for 3 protons, the sextet is for 2 protons, and another triplet that is for 2 protons. That's how you identify which peak is for which carbon. Now let's take another example. This is also a simple structure, CH3O, CH2, CN. So there are 2 types of protons attached to the carbon atoms. This is type A, type B. So this A will be a singlet because it is not attached to any carbon atom. It is attached to oxygen. So there will be no splitting. It will be singlet. Also for this B, it is not attached to any carbon which is attached to a proton. So it will be a singlet too. Now, solvent, like role of solvents in NMR. Solvent plays a very important role in NMR. The popular NMR solvents which we use in research is CDCl3, which is chloroform deuterated with deuterium, methanol D, that is methanol deuterated, and deuterated water, and DMSO. These are the most popular solvents used in organic chemistry. But there are other solvents too. Like depending upon the solubility of your compound, there can be a choice of a broad range of solvents and even mixture of solvents. So as I already mentioned, that solvents can change the chemical shift values of the protons. It will not change it abruptly, but it can change 4.5 to 5, like this. So some protons, like the acidic protons, alcoholic protons, and sometimes even the NH protons, they exchange with the methanol D solvent protons. So if you suppose you are checking and a structure with a carboxylic acid in methanol, so you may not see that carboxylic acid peak in the NMR because it exchanges with the solvent methanol D protons, so that peak will not be visible. But if you check the same NMR in CDCl3 or DMSO, you will able to see that carboxylic acid protons. So, and one more thing we must know, that no NMR solvent are 100% deuterated. So there will be maybe 99%, maybe 95%. So there will be a certain minimum percentage which is not deuterated. So we'll always see the NMR solvent residual peaks in our NMR. Sometimes these solvent peaks even interfere with our compound peaks. In that case, we are confused, like, are these peaks for a solvent or for a compound itself? In that case, you need to check NMR in a different solvent. And also, like, we use different kind of solvents during our synthesis and purification procedure. We use a series of solvents, and if you do not dry our compounds sufficiently for a long time, we'll see all of those solvents impurity peaks within our NMR. So it is very important to dry our compound for sufficient time before we check our NMR. And also NMR is very sensitive. It can even trace any of the impurities you have in your glassware, in your RBs, in your column, whatever. It can catch any impurities. So be very careful during your synthesis and purification procedure if you want to get a good NMR. So now I am going to show you a series of tables. These tables I have taken from a journal of organic chemistry paper, where they have precisely discussed the impurity peaks and the solvent peaks we usually see in a proton NMR or a 13C NMR. As you can see in this table, this is for proton NMR, the solvent residual peaks. I'm sorry. So the solvent residual peaks, let me go back. I'm sorry for this. Yeah. So the solvent residual peaks for proton NMR in different solvents. So this is CDCl3, this is CD32CO, this is CD32SO, C66, CD3CN, CD3OD, D2O. These are the different type of solvents, and this is the column for the impurity peaks. So if you are looking for specifically, suppose in CD3OD, so that is methanol D. So you look at this column, and suppose you have got any of these values in your peak which you cannot assign to your compound peaks, then they must be a solvent peak or a impurity peak. So if you are taking solvent in methanol D, you just check this column, or if you have any of these data which you cannot characterize for your compound, they must be for either the solvent or the impurity. And remember, like for methanol D, if you have a water impurity, you will get a signal at 4.87, and its multiplicity is singlet. If you have taken an acetic acid, it will be 1.99, that is also a singlet. Like this, these are for all the solvents. Like for tertiary butyl alcohol, there will be two type of protons, CH3 and OH. So you will see this CH3 signal for this methanol, because as I said that alcohol, carboxylic acid, aldehydes, they exchange proton with this solvent. So you will not see this OH peak here, but you will see this OH peak in other solvent like CD3CN, like CDCl3, etc. So similarly, if you get tertiary butyl methyl ether, you will have a impurity peak at 1.15. If you have cyclohexane, if you will have an impurity peak at 1.45, like this. So this table is very, very, very important. All these tables I'm going to show, they are very important. Like in NMR, you get multiple peaks there, and we try to assign all of the peaks with our characteristics protons within our compound, but there will be extra peaks. Trust me, there will always be extra peaks. So where are you getting those extra peaks from? So that is why it is very much important to go through these tables. And this is a very popular tables which we get from a JOC paper, Journal of Organic Chemistry. And most of the organic chemists know about this paper. I have collected it from there. So the main thing is that whenever you are getting something, a peak which is you cannot assign for your compound, there must be some solvent peak or some impurity peak. And then just follow this table. This is very simple. And then you take the solvent you are using and you just go through this column, like, and you check which kind of solvents or any other impurities you have used for your synthesis procedure, right? So this continues. You see there are a series of compounds in those different solvents. These are all solvent peaks or impurity peaks. And this is continued. This is continued. Now these are the signal impurity table for 13 CNMR. The same thing will happen which happens in proton NMR. Like you will always get some extra peaks, and which peak you cannot assign with your characteristics carbons, you will just check it here whether you can assign them for any of the solvents or impurities you have used during your synthesis procedure. So the rule is same. You just check the solvent which you are using for taking NMR, and you look for the impurities or other solvents which you have used in your synthesis procedure, right? So this table continues. You have to check all these. Okay, so I think these tables will be a great use to all of you. You can check it. And now let me show you the specific solvent proton NMRs. I am showing this to you because I have checked the solvent NMRs itself, like taking the solvent only without any compounds. So this is as you can see, this is a CDCl3 NMR, and this is, you can see there is a peak at 0, at 1.5, and 7 point something, 7.2 or something. So these three peaks are due to the CDCl3 solvent itself. So this is something whenever you are taking any NMR in CDCl3 solvent, you will see these three peaks present. All these three peaks will always be present there. Now suppose you are taking an aromatic protons, like a compound having aromatic protons, so this peak will definitely interfere with that. So suppose you have a structure with 6 aromatic protons and you are getting here a cluster of structures which has 7 or even 8 aromatic protons. That means your structure can still be correct because you have characteristic of 6 aromatic protons, and this CDCl3 is included within that, so it just enhances the value. In that case, if you are not sure whether this is for your compound or this is for CdCl3, then you have to check the NMR in a different solvent so that this peak doesn't interfere with that. And most of these, like 1 to 2, this peak also interfere for many of the aliphatic carbons. Like a good example is, I would say, tertiary butyl protons. It has a chemical shift value of 1.5, and this exactly interferes with that. So if you are checking NMR of any uh, compound having a tertiary butyl group, this peak will definitely interfere with that. So then in that case, you have to check your NMR in a different type of solvent. Similarly, this is a this is the NMR of a methanol D solvent. As you can see here, it has a peak of 3.3 and 4.9. So if you are having a compound which has characteristics peak in this region, these peaks will always interfere with that. So in that case, you have to check the signal in a different solvent. Otherwise, you cannot be sure whether the peak is for your compound or this is for a solvent. And one thing that is very interesting I would like to share is that whenever you integrate the compound peaks, I will show you like the characteristics compound NMRs, how do they look like. I'll show you step by step. So whenever you integrate on the peaks, and you will get some reasonable value like 2, 3, 4, 5 like this, and you can check with your structure whether it is matching with your structure or not. But whenever you integrate the solvent peaks, they will give you some absurd value like 45, 53, 110 like this, which are very, very absurd. You just do not assign those peaks to your compound peaks. There must be some solvent or impurity. Okay. So I would like to stop my lessons today in this, and I will be continue my next lesson in my next video. And please do subscribe to my channel, and you are welcome to post any query in the comment section, and I'll try my best to answer all of them. And thank you very much for your attention. Okay.